So, welcome back everybody, and finally in person. So the plan today is to bring up where we started last week on where we ended last week on resampling methods. And these resampling methods are very important in machine learning. So this is still this session 4 to 5, as we call them. And we are going to go through some of the basics of these resampling methods, and there are two main methods which are widely used. One is called the bootstrap method, and the other one is the cross-validation method. And last week I sketched what they actually imply from a computational point of view. So today we are going to look at how we can implement them, and we are going to discuss why we should use this. So one of the main motivations is the following. When you have a data set, this is a data set you have. And in many cases, if you take away the kind of simple vanilla cases, which I've been showing you with the simple polynomials, where you can generate again and again more data. So typically when you run machine learning codes, you try to split the data in train and test. And the amount of data you have is normally constrained by the data you got in, right? So if you do a medical survey over heart disease over 3 decades, you may follow something like 10,000 patients. And that means that when you want to make the data analysis, it's very unlikely that you will wait another 3 decades, right? Or if you run a nuclear physics experiment, typically an experiment runs for a week. And to set up the beam and everything is something which lies in the millions of euros of expenses. So if you fail, then yeah, that's your problem. It's very unlikely that you will get more beam time unless you can claim that you're pretty close to a Nobel Prize in physics. But if you have run an experiment, the data you have is what you have. That means that what you would like to do then, when you do the statistical analysis, is that you would like to provide a good estimate of the expectation values which you compute. That means that if you compute the mean value, we are always constrained to look at the sample mean. That's a quantity you're familiar with, right? So feel free to stop me if something is unclear. So the sample mean is the data you have, and you calculate the mean value by simply taking the average over all the values you have. You don't know the probability distribution. So that's one of the problems which we have. So let me just bring that argument quickly up so that we are on the same ballpark, all of us, before we start looking at these resampling techniques. So let me just bring that up. So if you want to calculate an expectation value of a quantity like a variable x, we know that if we have a continuous function, and we have the probability distribution, so this is over domain D, where x is defined, then this is given by a probability distribution and an integral over. You're familiar with these kind of expressions, right? And we normally call this the mean value. And I'm going to put a subscript x to indicate that that's the mean value with respect to variable x. And if you have the discrete case, then this quantity is just a sum over I element in this domain D of events which you have, and then it's an x of I, and then the probability px of I. This is under the assumption that you know the probability. Normally we don't have it. So when you run a machine learning calculation, you are less interested in the probability distribution. That means that what we calculate is something like the sample mean of the sample, or just the sample mean. So this is a sample of data. So that means that we are going to calculate a mu of x, which is simply 1 over n, and then we have a sum over all the possible events which we have, and then we have an x of I. So when I say the sample mean, this is the quantity we evaluate. And this is normally not equal to mu of x. However, if you follow Bernoulli's law of large numbers, we are supposed, when n becomes larger and larger, we are supposed to get closer and closer to the true mean value. So in principle, machine learning, the traditional path, does not assume that we are interested or know the underlying probability distribution. So that's a general feature of what we might call traditional machine learning, which leads to what's called the frequentist approach, where you just look at the frequency of the data, you read in the data, you make a fit to the data, you have the input and the output, and with that fit, you want to make predictions. So that means you have a fit of specific functions, and then you try to make a prediction with that. That's the standard path in machine learning, and the interest in the probability distribution is normally not that present, unless we are moving into the field of Bayesian machine learning and Bayesian statistics, where we then are equally interested in estimating the errors, because when you have the probability distribution, you can calculate the standard deviation, you can calculate the mean value according to that distribution, and so on. So that means that when we now are calculating things like the mean squared error, which in a sense is an expectation value, so this is actually the expectation value of the vector y minus the vector y tilde squared. This is the way we wrote it, and this is 1 over n, and then we have a sum over I equal, actually we started with n I equal to 0. So this and y I tilde is our model squared. This quantity here, when we calculate it, we want to give the best possible representation of this quantity. And that is why we deal with these resampling techniques, because if you calculate this once with the data set you have, this may still not be equal to the true mean squared error, because we don't have the probability distribution. So you could think of calculating this quantity here with, if somebody gives you the probability distribution for the events, then you could calculate this quantity with the right probability distribution. Does that sound reasonable? So because then you could actually go back and take these equations here and calculate the mean squared value with the probability distribution. But we don't have it unless we run a Bayesian calculation where we extract a probability distribution. So this means that in standard machine learning, we are just stuck with the data we have. And then we have to think of methods by which we can make a reliable estimate of the expectation values. So you could now say that these resampling methods, the aim behind them is to, with the little data you have, resampling methods aim at giving, at arriving at a, what I would call a reliable, and then we have to discuss what is meant by reliable, estimate of various expectation values. And you see now much of the weakness which we face when we are dealing with these methods here, that we don't know the probability distribution. We are calculating just a sample average. And in some cases, you may just have a few hundred observations. And it's very unlikely that you will be able to get time to obtain more observations. So if you run a calculation in lattice QCD, a typical calculation runs for several months, and you may just have some 500 to 1,000 output values. And then you want to make a statistical analysis of this, and that's why these resampling methods come in. So typically, if you now do a resampling like a bootstrap method, you would calculate the mean value for each bootstrap. So a bootstrap is simply you taking your data set and picking randomly among the data points with replacement. And you can do this random selection of data points as many times as you want. Normally people do that less than the number of data you have. So if you have 1,000 data points, you could resample the whole data set 100 times. So resampling means that you have your first data set, and then you make a new data set by picking randomly the different input and output values. And when you pick them randomly with replacement, it means that you can pick the same observation more than one time. So the bootstrap is a method which you can show actually converges to the correct expectation values if you have identically distributed and independent events. This is what in statistics is called IID. That means that all the events have the same probability distribution. So you're probably familiar with grading, that one wants to have a normal distribution on the grades, right? Have you encountered that situation? Often people, the ministries of education want grades to follow a normal distribution. That means that you all guys are identically distributed and totally independent of each other. And you can obviously question that, right? You can question that, especially when you look at the Master of Science degrees, because many people actually want to have a normal distribution of the Master of Science degree, which may not be correct, because often the people who enter a Master of Science program, there's been some kind of, selection process, and most of the people who begin with a Master of Science degree, they have an average of B. So if you then, on the master degree, you want to give people a grade which follows a normal distribution, then a big fraction of the people should have a C, right? And if you come from your bachelor degree with a B as an entry point, it would be totally wrong to actually give people a C on average, right? So you see the usage of this distribution is something one has to do with care. But normally with big data, and you're probably familiar with something which is called, are you familiar with the central limit theorem? Yeah. So the central limit theorem is the one which tells you that given an independent and identically distributed set of events, and your initial distribution doesn't need to be a Gaussian. It could just be a distribution which contains independent variables and identically distributed. Then that moves towards, when you go to large data set, it will approach a Gaussian distribution. Yeah.
So, talking about the resampling techniques, what, in your experience, what is the size of the sample for which it makes sense?
That's a good question. So typically if you think of the bootstrap methods, the bootstrap method is used up to samples of something like 1,000 to 10,000. Normally, when you have few data, what you're going to see is the following. When you do, suppose now that we do a bootstrap, and let me quickly remind you of the bootstrap. The algorithm is extremely simple, and we're going to look at examples pretty soon. So let me try to answer your question by setting up the bootstrap case and see what you're going to get. Because in many cases, you don't know the answer a priori. So with machine learning, you will have to rerun things many times. That's an important thing to keep in mind. And we are going to introduce more and more fitting parameters, which are often called hyperparameters. And to some people, it's pretty disappointing that at the end, you just end up tuning tons of parameters, like you saw with ridge and lasso regression. But let's now look at the bootstrap first. So we have a data set, and let's suppose this data set is now given by, just to make life simple, we just have the x's here, up to some xn minus 1. So this is our data set. This is the first data set. This is the one which you get. And then you would typically calculate, suppose now we are just interested in the mean value. So then you would calculate the mean value. So I'm just going to put points here, calculate mean value, mu, and of x. So that's the first point. Then, in the next case, what we do then is that we reshuffle the data randomly. We pick randomly, pick x randomly with a replacement. So with replacement means that you can pick the same data point again. Pick x randomly with a replacement. And then we get a new data set, D star, which is now given by an x0, an x1, up to an xn minus 1. So this is now a new data set. And some of the points there can be equal. Then you can calculate again this mu of x, you get star. And then you simply repeat 2 b times. Then the final expectation value at the end, you calculate final mu, which is now going to be a sum over b, and this contains now a sum j equals 0 up to b minus 1, and this contains all these values, mu of x as a function of this variable j. So each variable now is the one you have calculated for the reshuffle data. So the algorithm is extremely simple, and I'm going to show you how you can set it up. So this is a way by which you now can calculate the expectation value by bootstrapping. In Python, there's a simple function where you simply pick randomly a given number in a set of data. So I will show you in the codes how you can do that. So suppose you calculate now the mean squared error. So suppose this b is equal to 5, and we calculate the mean squared error. And then we do the mean squared error for the test case, or the test data. And suppose now we do these calculations here, and this is back to your question, because we don't know exactly what it's going to look like. And we are going to plot the mean squared error as a function of model complexity. So if you're dealing with a polynomial, this could be a polynomial of a given degree. So I'm just writing along the x-axis here, model complexity. So this could be a polynomial approximation. So the model complexity could be a polynomial of given degree. So what you would see then, if you do the first one, b equal to 1, it could perhaps go like this. So this would be b equal to 1. Then we make a new calculation, and this could go like this, and it could change a little bit. So this could be b equal to 2. And then we rerun a new bootstrap, and then we could get something like this, and b equal to 3. And they're going to change from bootstrap to bootstrap. The more data you have, the closer they will be. So if you have little data, these curves can actually vary. And remember now that, again, that what we have is a data set where we have, this is on a test case, and we can reach a point, this point here, where we have the optimal mean squared error. So this could be our b equal to 4. And then we run the final case, which is this one, and that could look something like this. So this would be b equal to 5 as a function of the model complexity. That means that you have a range of values which go in this domain here. This is your range of values. And then the final result is going to be the average of all these. So if you go back here, you see that the final expectation value we calculate is the average of all these calculations which we did with each bootstrap. So it means that the final value could be something which looks like this. So we could now make the final value. This could be the one which goes here. So this is the average of all the measurements, or all the bootstraps. That is the value you would present to your friends. You have a question? Is it clear, the work we're doing? So the bootstrap is a way by which we actually can estimate an expectation value, hopefully in a more reliable way, with little data. And clearly you see now that the difference in the curves here, this difference you see here, this difference is going to be smaller the more data you have. So if you have few data points, 100 to 1,000, then clearly you may get a larger difference. And then you would have to play around with different bootstrap calculations. So people often run as many bootstrap as you have data points. That's a pretty common thing. And typically, if your data is in the range of 100 to 1,000, then you will often use a bootstrap. If you have millions of data points, then there is another method which is called blocking, which is more used and where you can actually show that you reach the expected values, the proper expected values. If somebody gave you the distribution and you could calculate the exact mean value, these methods are actually supposed to reliably approach the true values. I'm not giving you the proof of it, but I'm just simply stating that there's a theorem for bootstrap which shows you that you can actually reach the exact value for a given distribution. However, we will always suffer with the fact that we are with a limited data set, and that means that this kind of situation which you see here, this one is something you will experience in many, many cases. This applies also to the method which is called cross-validation, which we discussed last week, which is also one of the popular ways to resample the data. But the overarching aim is to, with few data, to be able to make a reliable estimate of expectation values. Sometimes you don't have an idea what is a reliable estimate, unfortunately. But this is the often one of the kind of things we struggle with when we deal with machine learning methods. And at least there are theorems from statistics which show you that in the limit of large data sets, you will actually approach the true expectation values. So why should we care? Now, one reason why we should care is that we want to present a reliable mean squared error for the data which we have. So when somebody is going to use our model, we want to tell people, this is the model I trust the most. And it's as simple as that. So when you now at a Friday party, you want to present your best model to your friends, maybe that's nobody invites me anymore to parties. But if you want to present that to your friends, you have to really convince them that I've done my best possible when it comes to the statistical expectation values. Okay, so Bootstrap is very simple to implement, and we're going to look at examples now. And when we are running the projects, both project 1 and 2, you have to do a resampling. And in machine learning, the way this is normally done is either you write your own code, but since you guys don't have that much time, what I would suggest is that you use the functionality of libraries like scikit-learn. So you can write your own cross-validation code. It's not very difficult, but since we are short of time normally, and this is 6 credits, right? So I would normally recommend that we use the functionality which is baked into libraries like scikit-learn. And as I mentioned, this library scikit-learn is also a library which interfaces with other machine learning libraries. Like if you think of TensorFlow or PyTorch, you can use all the functionality, prepare arrays, reduce the dimensionality of matrices and so on, and then feed them in to other methods, other libraries, because scikit-learn has a limited set of deep learning methods. It has a very simple neural network, but it doesn't contain convolutional neural networks, recurrent neural networks, and more advanced machine learning methods. But then you can use all the functionality and just prepare your data, scale your data, and feed that into more advanced libraries. But these libraries are always expanding. So there are thousands of people which contribute to the development of these libraries. So sometimes it's okay to write your own code, but many of these codes are really streamlined for high performance computing. And when you have thousands of people at Google and Facebook which are developing these codes, clearly there's a most likely, like the codes I've written, they cannot compete with speed when it comes to the codes developed by thousands of good programmers. Okay, so I just wanted to quickly remind you of the cross-validation method. So just to remind you quickly about what we discussed last week. This is another method, and you will often see that in programs, that you will see something like a subscript CV. So if you see ridge CV, for instance, or lasso CV, that means you run a calculation with the lasso method and you include cross-validation by default. And it has some default values which you can change. So the cross-validation case, there's one quantity which is normally called the number of folds. We call that K. And that is the way you split your data in. And typically, if you have K equal to 5, and we discussed that last time, so I just wanted to quickly remind you of it so we're on the same page, all of us. You would split your data into 5 slots. And I'm going to use colors here, so the test data is in red. And then I use the orange one for train data. So with that one, it means that the first 5 slots now could be train, and the final one would be test. And then you can repeat this exercise 5 times. Actually, you do this 5 times. And then you would have now your test, your train, and train, and train. So you can do this shuffling randomly, or you can do it in sequence. And in each case, you would now calculate a mean squared value. Here, on test, you train a model, you calculate a mean squared here. On test, you do the same here. You do the same on training as well, because often it's interesting to compare the training error and the test error. And in this case, we would now reshuffle the data. So scikit-learn has a functionality which reshuffles the data for you, and it splits the data in these different slots. So I'm just going to redraw everything here. So let me just put this one. And we calculate the MSE again. So we can calculate this as MSE 1, 2, 3, 4. And let me do the final one, which we just call MSE 5, because we have K equal to 5. So these are 5 folds. And then we put in the test data. So we would have test here and finally here. And then we have the training data, which we use to train the model, like this. So we could then calculate again the mean squared error. So the mean squared error in this specific case, or we are not limited to the mean squared error. So that means that the final one is simply going to be equal to 1 over 5. And then I have a sum from 1 to 5 of this MSE of I here. And they can be done both for the training and for the test data. And this is the quantity you typically would then evaluate and present as your final mean squared error. Now what you have to play around with is the number of folds, because if you have few data points, what you can quickly see then is that these mean squared errors may actually change from one case to the other one. So you will again, if you see when you calculate these different mean squared errors, you may see a big variation. If you have a big variation, that means that you need to change the value of K, the number of folds. So it's not given that when you run this once, that it will actually give you a mean squared error which is nicely along with some few differences. You can actually get large differences for every training set which you have here. So these are things you need to play around with. So it's not given that you will get a nice mean squared error as a function of k equal to 5, and then you go to k equal to 10, and they're almost the same. They can actually vary. So this k, the number of folds, becomes a new parameter, which normally people play around with till this mean squared error stabilizes. If you have tons of data, there is no problem normally, because then if you have tons of data, that means that you're approaching more and more a reliable estimation of the mean square error. So in the examples I've shown you, which we normally call vanilla cases, we have data which we can regenerate again and again because we have simple polynomials. And that's normally not the case. So in this particular case, what you will see then, when you then plot the final values, what you want to plot then, again, as a function of the model complexity, so I'm plotting the values of the mean squared error for training. So orange is training, and that will normally go like this. So this is a train case, training. Oops, sorry. But the training case may actually have large variations among the different measurements. And this is something you need to study when you run the cross-validation calculation. And then what you would see for the test is that these will typically follow each other when you have a low complexity, but then you reach a point where you have overfitting. And we are coming back to this today. So this is a kind of, without mathematical proofs, that these methods actually give you the correct expectation values. I'm just telling you the way you can implement them. What we're going to do now is to switch back to the Jupyter notebook, and we're going to run calculations and just see that we can get what we expect. And then we are going to introduce something which is called the bias-variance tradeoff, which is something which is widely used in machine learning to get an estimate of whether we are overfitting or underfitting. Because you can make a model which is perfect on the training data. So you can train to perfection. You can, if you do a polynomial fit, you can actually just increase the polynomial complexity, and you can have every point in your model to go through the data points which you want to reproduce. However, if you then want to apply this model to something which has not been included in the training data, you will fail miserably because you have tailored your model to really reproduce that specific data set. And then when you use your model on something which was not in the training, you will actually fail. And this leads normally to overfitting, which is pretty common. So if you want to fit just that data, then there's no problem with overfitting because you're just having that data and you don't care about anything else. Then you can easily just use all the data as training data. The reason why you split in train and test is that you have a limited data set. So you cannot produce new data. And then you do this exercise with splitting some of the data into training, and then you leave the other points as something which has not been included in the training, and you want to test that or not. So everything deals with the amount of data which we have. And you will see that quickly now, that when we are running calculations, the more data you have, the better you obviously do on both training and prediction. Any questions so far? Yeah?
When we do the bootstrap, for example, and we calculate, so we would sample and we take a reduced sample of our data, and then we would calculate the parameters that we need. And then when we calculate the mean square error, which is the one that we afterwards average, we calculate it with respect to the full data set or just with the parameters that we found fitting?
Just with the parameters which you had. But you would train it on a limited data set, not on a full data set. So you always split your data in training and test. So the training is done on normally 70-80% of the data. And for every model complexity, as you see here, This is something which you also need to test. So when we're dealing with a polynomial, the model complexity in this case is actually the polynomial degree. If you deal with a neural network, it's the architecture of the neural network, which is your model. So that means the number of hidden layers, the number of nodes you have, that defines your architecture and your model. So we always define a model. So when I say model complexity here, it is just something which we have to define with the model which we have. So if you have a polynomial fit, then the model complexity is given by the polynomial degree. If you're dealing with deep learning methods, it's the depth of a neural network and the architecture of the network, which then defines your model complexity. And this is something which we have to play around with, because we don't know a priori what is the correct model. We can also have a perfect fit to the data, but the model may not make any sense physically. So that's also situations which you can encounter. Okay, let's switch back to the notebook here and just take a quick look. So let me just bring that up here. And let's try to make this a little bit smaller. Do you see well? Is it good enough? Okay. So I'm going to show you, so since everybody seemed to know the central limit theorem, which is very important, I just wanted to state the results here. So what you will end up with, if you have a distribution of the independent and identically distributed events, these will approach a normal distribution where the mean value is the sum of all the mean values divided by number of data. And then the variance which you have and the standard deviation is then given by the variance of the original distribution divided by the number of events which you, or the number of events which you calculated. So suppose now that you run an experiment m times, and the original experiment had a variance which was sigma squared. Then when you run this m times, you're going to narrow down the variance. So what you're doing then is actually your variance is becoming smaller and smaller. The mean value stays the same. The mean value cannot change. But the variance may become smaller and smaller. That means that you narrow down the standard deviation. And if you now look at this, so what it says that in the original distribution, you could have a standard deviation which was given by sigma. And then when you run this experiment many, many times, so suppose you count or you do some tossing a coin every day, and you know that you roughly should get 50% heads and tails, and you do that again and again and again and again, then you can really, when you've done this 10,000s of times, then you can really narrow down the number of, because when you do it tossing the coin only 10 times, you can get 8 heads and 2 tails. But if you do it 10,000 times, then you will be 97% sure that you will get the 50-50 case. So that means that you're narrowing down the standard deviation in what you expect to see. That sounds reasonable, right? So if you do few experiments, they can deviate from what you should get. If you run this many, many times, you should get closer and closer to the true answer. And here's a simple code here where I actually set up a example of how you would use the bootstrap. So let me just go down here. So in this case, I am generating a data set with a normal distribution with a mean value of 100 and a standard deviation of 15. So if I have 10,000 data points and I do 10,000 bootstraps, so that means I take my original data set, which has 10,000 points, and then I produce 10,000 new data sets by using the bootstrap method. So I could have done it differently here. I could have calculated 10,000 new data sets with a normal distribution, right? That's one way of doing it, because this is easy to calculate. But what I'm going to do now is actually to generate these by the bootstrap method. So instead of me calling the normal distribution, which you can see here, so this is my rand function, normal, with the data points. So here I produce the distribution with a mean value here, and then I have the standard deviation, which is now 15. So if I redo this 10,000 times, I should get a standard deviation, which is 15 divided by the square root of 10,000, if I believe in the central limit theorem. So I should then get 15 divided by 100. And the mean value should stay the same. So each one of these cases here will generate a slightly different mean value. So what I'm going to look at now is the distribution of the mean values, which is actually what is defined by the central limit theorem. So in this specific case, what I'm doing now, this random distribution here is given by the function randint. This picks a number randomly among the n data points I have. This is the way you would do the bootstrapping. So you have a data set with 10,000 points, and you just pick randomly. So you make a new data set. So in this case, you could actually, since this is a vanilla case, you could actually just call the normal distribution 10,000 times. But now I'm bootstrapping 10,000 times. And if I run this code here, by producing that and calculating the mean values, what I'm actually getting then, so this takes normally a little bit time here, you see now that since I have only 10,000 data points, I'm not going to get 100 exactly. So this is my original data set, and this gives me now the original bias, the standard deviation, which should be 15, but it's not exactly 15, because I have a limited data set. And then I do my resampling again and again. So my standard deviation, my error now becomes closer to 100 by accident. It won't be that next time I run it. And then you see that my standard deviation follows the central limit theorem. So I've done this 10,000 times. So I actually can narrow down my uncertainty in the mean value. And you can see now that now my mean value, instead of having a standard deviation of 15, which means that you would have gone, if you go 67% out here, you should have gone 100 plus minus 15. Now in my case, it's 100 plus minus 0.115. That's the ideal. So this is just a simple demonstration of the central limit theorem by bootstrapping. You could have done this exactly what I've done here by simply calculating 10,000 times a new normal distribution. But this is a demonstration of what the bootstrap is doing. So the bootstrap actually approaches the true mean value, and it follows the central limit theorem. So it's narrowing down, it's producing a distribution of mean values, and it's narrowing down the standard deviation. So that means that when you use a method like bootstrap, what you can claim then is that your mean squared error should narrow down its own deviation. So you calculate a mean squared error with a standard deviation which becomes smaller and smaller. That's the hope. So it's simply an application of the central limit theorem. But then there is another thing which we need to discuss now, and that is, yeah?
If you are using your data sets and just vary them to get narrower,
yeah.
If your data set has is not accurate enough,
yeah.
Isn't it worth to make a prediction?
Yeah.
You narrow in your data, but you cannot extend.
You don't know that a priori. That's the problem. So you will simply have to play around with different bootstrappings or different methods to resample your data set. So this is one of the problems you face, is that you don't know a priori how this kind of resamplings will behave. And that introduces a new set of parameters, like when you do cross-validation, you would have to play around with a number of folds in your data set. So this is actually one of the things we have to live with when you do machine learning, especially if you have few data points. I hope that answers the question. I mean, this is actually one of the more delicate things, because the next point we are going to look at now is this bias variance trade-off. And we should take a small break soon, but I wanted to bring up an image here. So you can actually show that you can rewrite your mean squared error. So typically the applications of the bias variance trade-off are normally shown from a pedagogical point of view in connection with the mean squared error. So you can show, and I'm going to give that as an exercise in the first project where you have to derive this. And we can discuss the derivation afterwards. But you can split it into what's called the variance of the model itself, the standard deviation or the variance from the error, the noise which you have, and then a so-called bias, which measures the deviation from the mean value of your model and the data you want to reproduce. So let me show you that in an image here. So the ideal is to have a low variance in your data set. So this is the dots here, the blue ones. So what you want to reproduce is the red area. The blue ones, that's your model. So if there is a small variance in your model, that means that there's a little spread in the predictions you make. Are you with me with that? So small variance in your model means that the data points you predict, they don't have a big spread. Low bias means that the mean value, if you calculate the mean value of all the points in your model, then that mean value is close to the results you want to reproduce. So this is the ideal situation. So it's called bias because it shows you how biased you are in your model with the mean value as a deviation from the data you want to reproduce. The variance in the model in itself is also important because if you have a large spread in your model, this is typically where you end up overfitting. So if you look at the high variance and low bias, so low bias means that you're close to the data you want to reproduce, but then you have a high spread in your model. So high variance means simply a high spread. And this is an unwanted situation, but this also kicks in often when you have overfitting. And then you have a high bias, but low variance. So your model has a low variance, but you deviate a lot from the data you want to reproduce. And then you have the next case where you have a high bias and high variance. So this is a case where you're just far away. So you don't hit the point and your model has a large spread. So what we're going to do after the break, we're going to look at examples and see how we can actually visualize this in connection with overfitting and underfitting of the data set. Yeah?
But in reality, you can never know how much bias.
No, you don't know. You don't know. You have to really run the model calculation. And these results will depend, as you will see after the break, on the number of data you have. So you will see that these kind of statements, how this behaves, is data dependent and model dependent. And you don't know a priori how it will behave. And that's why in machine learning, you don't run one calculation. You run zillions of calculations. And then from these calculations, you have to extract what is the best model for that data set. So when you run neural networks, for instance, deep learning methods, you actually rerun this with many different model architectures. So it's not, you don't know the answer a priori, unfortunately. Should we take a break, guys? Small break? Stretch legs, grab some coffee. Okay. So what we discussed before the break is, so what you can do, and I just wanted to bring back some of the definitions here. In a sense, when you do linear regression or any of the machine learning methods, like also logistic regression, we are making an assumption. And that assumption is that the data we have are given by some function f of x. So we assume that this function exists. This is for regression. It's assumed to be a continuous function. It's assumed to be a deterministic function. So you feed in some variable x and you get an output y. And we assume that this function exists, and then we have to make a model to find this function. But keep in mind that there is actually an underlying assumption here where we have assumed that this f of x is a deterministic function. We can make this more complicated and assume that this is given by a distribution. So when you're meeting logistic regression, we are going to change f of x with a probability. If you do Bayesian machine learning, you could actually define a probability. And then you could think of x as a stochastic variable. But what we are doing now is to treat x as a deterministic variable. So suppose you have a beam of particle, then the assumption is you feed in the beam and something happens, which is y, right? The variable on the left-hand side. So this beam which we feed in is so well defined that we know all the values of x. They are predetermined. So there is no stochasticity with the x's. So this is an underlying assumption. And when you do that, when you look at the mean value, or no, not the mean value, but the mean squared error, what you can do then is that you can add and subtract the value, the expectation value of y. So actually what you're doing now is add and subtract this expectation value. And then when you write out the squares, you can reorganize everything in terms of this bias and this variance of the model itself. So this is just treat this as a way to interpret your data. And it has this nice, if you think of this figure here, then you can easily translate this bias and variance in terms of you making a model which has as little variance as possible within the model, and then a model which really gets close to the data you want to reproduce. And that's called low bias and low variance. And obviously what you have here to the upper left is the ideal. That's what you want to reproduce. Now, what I wanted to show you now is a simple example where we apply the bias-variance trade-off with Bootstrap. So with Bootstrap, it's easy to do it. With cross-validation, you need some rethinking, because now, if you look at these simple models, I'm just going to scroll down here. So what I've done now is normally what people do, and there is no golden rule here, but often what people do is that they have more bootstraps than data, or as many bootstraps as you have data points. And here's my vanilla case. So this is just a function y, which has some random noise, as you can see. And you can run these Jupyter notebooks yourself because you have access to all the material. X goes from -3 to 3. And then I have my y, which is just e to the minus x squared, and then some other exponentials. So what I'm going to do now is to make a polynomial fit to this data, okay? And I'm going to make a polynomial with max degree equal to 14. So I want to fit a polynomial to this data set. And I split my data in training and test. This is standard machine learning functions. And this is a train test split, is a function with scikit-learn. And this function interfaces with the PyTorch, which was developed by Facebook. It interfaces with the TensorFlow of Google and many, many other machine learning libraries. So you can use all this functionality as it stands. Or you can write your own train test split, but there is no new insight in writing a train test split, because this is just you splitting the data. So if you can use something which you know how to do, there is no point in doing it. It's like you calculating integrals. You know how to calculate integrals. So if you can calculate it with Mathematica or symbolic and manipulations or numerical calculations, then you would do that, right? Because that saves you time. this is a digression. When I began my first year at the university, I loved solving all kinds of integrals. I just looked at the integral and then I knew exactly how to solve it. But it didn't give me any insight about what is integration. I was just learning recipes, right? And when I didn't practice anymore, I had forgotten all these kind of tools which I learned. But then when I took a course in numerical analysis, I understood what integration actually means. So when you have understood what it means, then calculating an integral is like it's like you using a hammer or a tool to do something. And if you can use symbolic manipulations or numerical calculations, you would use that. And so with train test split, these are functionalities which you should just use as a stand. And in this case, what I'm doing now is to do a polynomial fit. So I give the polynomial degree, I use linear regression, as you can see here. And then I include the intercept, fit intercept false. And here, what I do now is to simply perform a bootstrap and I resample. So scikit-learn has a function which is called resampling. And that does the bootstrapping for you. So that function there. So I feed in my X train and Y train. This is the data I want to use for training. So it simply does new data set with replacement and picks randomly the data points. So you can write your own, but when you have something like resample, you would rather use that one. And then you make a prediction. So this is my model, which is now being fit. And I do this 100 times for every polynomial degree. And then you see now that what I'm doing is now to make a prediction on the test data only. So I'm not plotting the mean, I'm not going to plot the mean squared error for the training. You could have done that in addition. That would just be another line here. But now I'm just looking at my prediction on the data which were not included in the training. So here I use the training data, and now I make a prediction on the test data. So just keep this in mind. And this is where you apply the bias-variance trade-off. And here I calculate the mean squared error by using the mean functionality. And then I calculate the bias. So this subtracts from the test data the mean value of the model, the prediction. And then I calculate the variance of the predicted data itself within the model. Now, if I run this, what you would see then when you look at the plot, so you can now see the values. And if I now shrink this a little bit, let me just shrink it a little bit more so that we can squeeze it into the screen, you will see something like this. So let me try to explain what we have. So you see now the green line is the variance of the model itself. So when you see now that for a given model complexity along the x-axis, this is a polynomial degree. So I had 40 data points. That's my data set. And what you see now is that when I reach a polynomial of degree 8 roughly, then the mean squared error starts increasing. So what happens now is that you're getting into this region of a high variance for the model itself. And this is a clear example of overfitting your data. So when you're reaching into this point here, around 8 degree of the polynomial of 8 to 10, if you go back to this image which we had, we are now getting into this region here. So we have a large scatter in the model, and that means we deviate a lot within the model itself. So we have many outliers when we test our prediction on test data which were not included in training. So that's a clear example that we are overfitting. We are not being able to reproduce properly our data. And what you see then, when you then scroll down here a little bit, let me just bring this window in here. I should have printed out differently. You see now the variance goes more and more down. And if you look at what we're having, so this bias-variance trade-off that summarizes this kind of fundamental tension in machine learning, in particular for supervised learning between the complexity of a model and the amount of training data. So what I'm going to do now is to change the amount of training data. So what I'm going to do here, if I rerun it, I change this now to, let's say, 500 data points. Let's do that. And let's see what happens then. And you get this. So you see now that with the model complexity up to a 14th degree polynomial, my variance in the model is basically 0. And I'm getting a pretty good mean squared error on the data which were not included in the training. So my mean squared error now, and this is done now with bootstrapping, predicts now a mean squared error which is still not 0, but it's pretty small. And you see now that when you increase the model complexity, and you know that we are fitting e to the minus x squared, so this is something which is a simple polynomial, and in principle you should have an infinitely many terms in the polynomial. So you should get, if I now increase the degree of the polynomial, this should become better and better with this large amount of data. So if we now go to 30, and let's suppose we take 1,000 data points, and then 100 bootstraps, what we get then is something which, let me see, now it takes a little bit more time. So let's just bring it up here. Still, now when I'm getting closer to 30, you see it's bending up. But the variance is basically 0, and the standard deviation has basically stabilized here within this value. So that you would say now that for a polynomial of degree 10, I have my best reproduction of this specific data set. And you would then say that there is no need in going into a more complex model because you're doing a pretty good job here. So these are also the kind of considerations you have to make when you're, yeah?
I have a question.
Yeah.
Because if we are saying like a priori our data can be fixed by a function fx,
yeah,
and it's continuous and it's smooth-wise, everything, in theory, with every we can have any function can be described as a polynomial of infinite degree.
Yeah.
So in theory, if I enlarge the complexity or the grade of the polynomial, it should be better. But why it happens then?
So why it
happened? When I increase the complexity of the model, doesn't happen.
So this depends on the number of data you have. So if I were to increase the number of data, so with 1,000, this seems to reach the best mean squared error here. So it doesn't improve. So if I want to get a smaller mean squared error, I would need more training data. So this is all done on the test data. So in this particular case, the test data is only 20% of the full data set. So if I were to rerun this, I could rerun this with a polynomial of degree. So I still keep it, but if I take 10,000 points, I should get an even smaller. And then I can also increase the number of bootstraps if I do that. So let's rerun that one. That's going to take a little bit more time, but still it's pretty fast. But you can see now that the total mean squared error is getting smaller and smaller, as you can see here. But it grows very slowly. You see this number here is actually the mean squared error. You see that just goes down and down here when you look at the numbers. On the figure there, you get a little bit deceived because the figure starts with a large value. But if you look at the numbers here, you see now that when I increase the number of data points, this is sometimes it can jump up again, and that happens, right? So this would be a typical case where probably now you are reaching a region where the amount of data you had gives a mean squared error which starts increasing, and that would be a sign that you are reaching into a region, and you see now it keeps increasing, right? So you have an optimal value here for the test. If I were to calculate this for the training, that would become perfect. So that would just diminish more and more because the higher the complexity, I'm only test. So this is an important point. If I do this on the test data, this will clearly be something which can change at a certain point. And that would be the place where you're starting to overfit. You don't see it so clearly here because you have so many points. But if I were to go to higher and higher degree of the polynomial, you would see, on a figure you don't see it, but if you look at the numbers here, you see now that this is starting to increase, right? But then it can decrease again. So you don't know a priori how it will behave, but you see that it starts increasing. And if you go down now, it's 0.01. But you had a minimum around here where it had its smallest value. If I were to look at the training data, this would go to 0. So that's the important thing to keep in mind, that the training data, you can actually fit the model perfectly to the training data. But it depends on how many points you have. So this kind of behavior now, if I now increase, suppose I go back here and I take less data, take 100 and do 100 bootstraps, then you would see something like this. And this, the variance goes up. And that's a clear example. So here you get a little bit cheated because this is 10 to the 7th, right? So you don't see what happens down here. So this kind of tension, as it says here, if you now look at the text which is here, it simply tells us that in order to minimize the expected test error, we need to select a statistical learning method that simultaneously achieves a low variance and low bias. And the variance is inherently a non-negative quantity, obviously, and squared bias is also negative. What you see then is that the expected mean squared error can never lie below the variance of the irreducible error. So the variance refers to the amount by which our model would change if we estimated using a different training data set. And since the training data are used to fit the statistical learning method, different training data sets will result in a different estimate. But ideally, the estimate for a model should not vary too much between training sets. However, if the method has a high variance, then small changes in the training data can result in large changes in the model, as you saw. So when I switched from 40 to 1,000 data points, there was a big change in the variance of the model. So these are the things which you have to play around with, and you don't know a priori what kind of behavior you can see and when you will start to overfit. So just to give you another example of overfitting, there is a simple function here. So I have a data set here where I now fit. Let me just show you that one and you will see that quickly. So I have a true function, which is the orange line, and I try to fit that with a polynomial of degree 1, and then you see a pretty large mean squared error. So this would be an example of underfitting. Then with degree 4, which is the degree of the polynomial, then I'm actually pretty close. I have some noise here. So it's not exactly a true 4th-order polynomial, but you see now that I'm doing pretty well, and I have a small mean squared error. This is a mean squared error, and this is the variance, which I calculate, giving the standard deviation. And then if I fit a polynomial degree 15, then you will see something which is interesting here. If you look at that graph there, you will see now that you are going to try to go through all the points in some kind of strange way. So you're trying to reproduce the points, but when you then want to calculate the mean squared error, you just fail miserably. So that's an overfitting case. And what you would see in that case, when you decompose this in bias and variance, is that you would get a huge variance. And you see that in also the way your model here is now given by the blue line. And if you calculate the variance there, that is going to vary a lot when you take the mean value for the model and calculate the variance for every single data points. And you can almost see that from the graph itself. So these are examples of, cases which you will encounter when you do machine learning. And when you're fitting something, you always vary about this overfitting problem and underfitting. And that's why people normally do this kind of bias variance analysis. Now, coming back to the projects, which I thought we could do, the first project, I wanted to bring in some basic elements, like this bias variance trade-off. And one of the options, since you guys are pretty heterogeneous groups, you have different needs, wishes, and things you want to do. I'm going to propose a kind of basic data set, and where you are going to study the mathematics of these different methods. You're going to analyze the bias-variance trade-off. But then, if you don't like the data set I'm proposing, you can try to change that, or you can add data sets which are closer to what you are going to do. So we always had a group, we already have a group here who have some data set they want to explore. So I just wanted to mention this now before we go into cross-validation, so that you can see the different options in the project. So this depends very much on where you are. So I can propose what I would call the classic path, where I give you the data set, and then we apply the different methods, or you can replace them with your own data sets. If you already have a project which goes in which moves into your master thesis. So I was thinking of having two projects, one which is more on logistic regression and linear regressions, which we have discussed till now. And we will continue with that in this afternoon with logistic regression. And then it will also include you having to write a gradient method. Because in linear regression, you can just invert a matrix and you have the parameters beta. But normally, you don't have such nice analytical expressions. And that means you need to calculate gradients numerically. And when you have to calculate gradients numerically, you open all the evil things you can think of in machine learning. And that is, you have to find the minimum of a function. This function is in general going to be a multi-dimensional beast, and you don't know whether it's a convex function, whether it has local minima, global minima, or whatever. You can be stuck in a saddle point and never move from that. You can be stuck in a local minima and never reach the true global minima, if there is such a thing. So when you do neural networks, you have millions of parameters. The cases we have now with a polynomial fit is something like 2, 3 to 30, 40 parameters. And that's a baby case normally. When you go to deep learning methods, you have tons of parameters. And then your cost function is an ugly beast, and you want to optimize that. And you want to do that efficiently. And as I said in the beginning here, if you can make some progress in this optimization method, which is really the bottleneck of machine learning, you're going to get many, many new friends. And these are friends which will cite you. So, and as I said, I'm not inferring that you don't have friends, but there is a famous algorithm for calculating the gradients, which is called the Adam method. It hasn't anything to do with Adam, but Mr. Adam, but it's an adaptive momentum method. And guess how many citations that has? It appeared in 2014. It has now 120,000 citations. A normal physics paper, a good physics paper, has something like 50 to 100 citations. That's normally something we call a good paper. We have 120,000. And that came in 2014. So that really tells you what is the bottleneck in machine learning methods. And this is the topic after the break when we're done with logistic regression. So the first project will contain some of these mathematical elements. But since I want you guys to have maximum flexibility, we can try to design, instead of having two projects, we could just have one big one where you merge project one with project two. So you could do logistic regression and linear regression and neural networks together. And then you would be just evaluated on that. Or we can just do two projects. And we put a kind of loose deadline for the first one by December the 15th. But what happens every year is that we normally, I believe strongly in procrastination. I think procrastination increases creativity. So the deadline is for your planning. Okay? But if something goes wrong, as long as we get the projects by the beginning of February, because you guys are leaving and going to a master project, and then you would like to have some final grades, right? So we would need it by, let's say, the end of January, beginning of February, so that we can get, yeah?
So I don't get exactly, what is the goal of the first project? We just develop the mathematical tools that you...
No, you're going to get a data set, and you're going to run a linear regression case with ridge and lasso on a function, which is a continuous function. But you could change that function with some real data. So it could be topographic data where you want to fit a landscape. Or you have perhaps data from an experiment. And then it will also contain you replacing the standard linear regression in matrix inversion problem with you calculating the gradient and finding the optimal parameters beta by numerical optimization.
So you just take a model that we think,
yeah,
that, like with as many parameters we want,
yes,
and
yes,
you just do
yeah,
like several fits.
yeah. So everything we've done till now, plus this optimization part, is going to enter project number 1. Yeah.
So normally, what in machine learning people do is like they have a data and they find models. So in our case, we have a model.
Yeah.
In that case, people are going to look for data.
Yeah.
That is going to fit their model.
Yeah. Yeah.
That's kind of weird.
Yeah. No, but it depends. So I would propose. So there are 2 cases which we normally have looked at in this course. So one is just a simple function, is a 2-dimensional function, which is just a sum of exponentials, and it's going to look like a landscape, and you're going to fit that one. So that's a kind of what we call vanilla case instead of the 1-dimensional cases which I showed you here. Because according to my wife, when I move beyond 1 dimension, I am on shaky grounds. But the 2-dimensional case is something which gives you this kind of feeling of how to fit a surface. Then I'm also going to suggest topographic data, where you actually have a landscape, where you have the height and the X and Y direction. And these are real data you can extract from a website. So if you have a strong, you're longing strongly back to home, you can actually zoom down where you came from and then get the topographic data of your hometown or your home place and then fit that with linear regression. That can perhaps soften the kind of homesickness, right? If that's a problem. But you can also think now that, okay, I don't like what I'm proposing, right? And I have my own data from an experiment. So I have the inputs and I have the outputs. And I believe that this data can be fitted by a function. And then you can run the same methods on that. So I want you to see this kind of flexibility in the projects. So I have to propose something because, I mean, many of you have never done machine learning before. And you're also a very heterogeneous group. So some people are happy with just what we propose. But some people have something they are more determined they want to study. And you guys can team up in groups. And if some of you have some exciting data and other people think, oh, that was exciting, I would like to collaborate with you. You can then form a larger group and collaborate on that data set. So I want these kind of projects to be perhaps close to some research direction so that you don't feel that we're just doing a kind of regular course. So one data set which people actually looked at last year, they actually took these nuclear masses and then they tried to fit the masses the best possible way. That's one option. Or people looked at separation energies and tried to fit them. So that's a more nuclear physics explicit case where you take real data. Did that help? Was the answer okay? Now, so just start thinking of it, right? I'm going to propose just a general project, and then you can replace the data, which I propose, with data which you think are more interesting to you. I hope it was not too convoluted, right? Okay. So what I wanted to discuss a little bit more is actually this cross-validation. And in this cross-validation, the basic steps, you would choose the number of folds, you shuffle the data randomly, you split the data into K groups, these are the so-called folds. And then for each unique group, so this should actually be inside here, you decide which group to use as a set for test data, You take the remaining group as a training data set, and then you fit a model on the training set and evaluate it on the test set. And then you repeat. And then you retain these evaluation scores, which you calculated for the specific test model. And then you repeat. And then at the end, you just summarize the model using the sample of model evaluation scores. So let me just show you a simple example here. So this is again a very simple function. It's not very exciting. It's just x squared plus some random noise. Not very exciting. I want to fit this with a polynomial of degree 6, which is not a very intelligent proposal of mine, because it's a polynomial of degree 2. So but I'm just going to do a fit to that. So in principle, and you will see what happens. And here I'm using ridge regression. So what I'm doing now, I'm having this hyperparameter lambda, and I just have a grid of lambda values from 10 to the minus 3 to 10 to the 5. So I'm using lambda as a hyperparameter. And you will typically see that people tune these parameters to get the best possible mean squared error. Then I'm using, here I actually made a function myself where I split the data, but I'm using scikit-learn's functionality. So I'm a little bit lazy. I didn't write it fully out myself. So I use this way to split the folds for me. And then I simply set up my training data according to the different folds. So I have 5 of them. I'm looping over the hyperparameter, that's the external loop. And then I loop over the folds which I have. And I do the training and testing. And in each case, I calculate a prediction. And I calculate the score, which is the mean squared error. So that's my own function. Then you can use the cross-validation feature, which is baked into scikit-learn. And when you're writing your projects, I normally recommend to use this functionality. It saves you a lot of time. And there's not that much insight in just splitting the data, like I showed you here. And scikit-learn has now first I do the ridge regression, as you can see here. And I perform, I have my data here, my design matrix. And then I feed in the method to the cross-validation score. So this cross_val score that computes actually the mean squared error for me now with the ridge regression case here. And it calculates the mean squared error, and it gives as input the number of folds which I have. So in this case, I have 5 folds. And if I've written my code correctly, I should get the same here. And you will see now that when you compare my own to scikit-learn, I get the same answer. Now, in this case, you see now that when I begin with a small value of lambda, this is what I would get with ordinary least squares without the hyperparameter lambda. And you see now that there is a dip here. So I'm actually getting a mean squared error, which is pretty small here. So this is the estimation from cross-validation. Now, what you're going to see for this data set clearly, where I was not very smart, if I now were to go back and say that I do a polynomial degree 2, which is the correct way to do it, and I rerun it, you will clearly see something like this, which is what you would expect, because now I'm having the right polynomial degree. And normally when you do a polynomial fit, what you're going to experience is that ordinary least squares does often the best job. If you're interested, we can discuss that a little bit later. There are some deeper insights about why that happens. But when you have data which are not fitted with a polynomial, where you can have columns in the design matrix with strong dependencies, normally ridge and lasso regression do a better job. But here you see now that they have a mean squared error, which is pretty small. And then it increases when I increase my lambda value, which means that I'm suppressing features in my ridge regression approach. Now, one thing you would also see is that if I now change, this becomes a hyperparameter. So what you would need to do now is actually to play around with that one and see if that changes. If your results change dramatically, it means that you would have to change the number of folds. And in this case, actually, the result didn't change that much. So 5 folds with this amount of data and 10 folds gave more or less the same mean squared error. If you were to decrease the number of data points, so here we have actually quite many. If I were to take only 30, then you could get a larger variation. So if you now run it, you see now you have roughly this value here. I'm going to reduce a little bit, so here we can see a little bit better. So let me just reduce this number of lambda values to just 10. And we are going to let this run up to 1 here. So we just reduce, or we can even make it smaller. Just let it run to -1. And now you see this is, you have a mean squared error with 5 folds, which is 0.99 something. If I now change my number of folds, actually this was 10 folds. So that means that I have taken 30 data points, divided by 10. So each slot has only 3 data points now. So I have only 3 data points for testing and 27 for training. And if I do 5 now, so that means I would have 6 data points for testing and 24 for training of the 30 ones. Then let's see what we get then. And now you see that the error has actually diminished. So when you have few data, but also in general, you should try to test the mean squared error you predict as a function of the number of folds you have. If you have lots of data, then normally you can just use 5 folds, which is the standard. There's a kind of rule of thumb, which is more the result of you practicing, which says that people normally use from 5 to 10 folds. That's a kind of rule of thumb. But this becomes a parameter, and you have to test it out. So machine learning contains a lot of this kind of, you playing around with your data set. And you don't know the answer a priori. The reason why I stress these things, I mean, it don't sound very exciting, but the reason why I stress it is because you, as physicists, you may be the people who actually develop the next generation of machine learning methods. And then it's important for us to have a deeper understanding of what enters. We are going to use the libraries because they are convenient. They are tailored to high performance computing. If you go into the GitHub address of scikit-learn and TensorFlow, you will see thousands of people contributing to code development. So this means that these are highly tuned libraries and written in the most efficient way we can think of, tuned to run on high performance computing facilities, which means then again that we should use them unless you believe yourself that you can write better code than thousands of programmers in Google, which is possible. That happens. But these are highly tuned libraries, and I would use them, but you have to understand what enters. That's the important thing. And then when you understand what enters, it's much easier to see where you can make important improvements. And in machine learning, there is now a whole field which is under development, which is called physics-driven machine learning, where you actually have physics input as input to machine learning methods. Many of the methods which have been extremely popular are methods which are tailored to imaging. So image recognition is something which has received a lot of attention, but this is often something which is void of physics input. These are just images of cats, dogs, and so on. If you have a physics experiment, if you run an experiment and you want to recognize different events because you have an image from your detector, so if you're looking at a charged particle that moves in a specific way in a magnetic field, and then from the image from the detector, you can actually say what kind of event that was. And that would be different images you could train a neural network on, and then recognize these images as a proton decay, as a carbon event, or whatever, depending on the charge which the particles have. or the objects have. Now, in the slides here, you will find more examples on bootstrapping and so on. And I just invite you to just take a look at them. But the basic idea of cross-validation is what is exposed in this simple example, which you see here. And I would simply recommend you to use the functionality which is baked in. And in this specific case, you specify the score function you want to look at, which is the mean squared error. And this actually does this automatically for you. And it does exactly the same thing which you see here, where here I actually have my own sum, my own function for the mean squared error. And then I do the splitting in train and test according to the different folds in my own code. But scikit-learn does exactly the same thing in this just one line here. And when you are going to run the codes for the different projects, I normally recommend to actually use this functionality. But what you have to be aware of is the fact that your results will always depend on the data set which you have. That's what's going to limit us in a way. And then you have to use these methods to gauge the quality of your model against different scores, like in this case, the mean squared error. So this would be the, I just invite you to take a look at some of these functions because I've actually baked in different examples with cross-validation. This is just a fit of a neutron matter calculation of the energy and the density, where I'm just exceeding the polynomial degree. Actually, a polynomial degree 5 is the one which does the best job. And in this case, I have 150 data points. And the results are going to be very sensitive to the number of folds which I have. And in this specific case, where I have I think it's 150 data points, you would then see something like this, the polynomial degree. So this was a data set with 180 points with 10 folds. And in this specific case, I'm running over the polynomial degrees. I'm performing a plain linear regression, as you can see here. I keep the intercept actually. And then I look at I perform my cross-validation, where now instead of ridge, I have an ordinary least squares. And that takes my design matrix, which is a polynomial to a given degree, with the density to a given power, and the energy per particle as the output I want to reproduce. And for this case with 5 folds, I found now that the polynomial degree 5 gives me on a test data a mean squared error, which actually you can see is pretty large, is roughly 5. So it's not a very good model. If I now do 10 folds and I rerun it, I would actually get a better mean squared error. So you would then have to play around with a different number of folds as well, and you would pick the one which gives you, as a function of polynomial degree, the best mean squared error. When you run into textbooks, these curves will always look smooth. In textbooks, life always is smooth. In real life, life is, not necessarily nasty, but it's more complicated. And your results will always look a little bit choppy like this. So I wanted to stop this part now, and then we're going to move into, after lunch, I wanted us to move into logistic regression, and then the real bottleneck of basically all machine learning methods, which is the optimization part. So I thought I'm just going to stop the recording just a moment, and then we can take questions here.